In this video, I'm going to introduce some important terms that relate to chemical energy. First, we're going to revise some of the concepts from Module 3. You should be familiar with the diagram that's on this slide. It's an energy profile diagram. It shows the amount of energy that the reactants have and the amount of energy that the products have. Some important features of the diagram are, first of all, the activation energy. That's the amount of energy that we need to supply to the reagents before they will begin to react. And then the other really important term is the enthalpy change. That is the difference in energy content of the reactants compared to the products. Now, in this case here, the products have less energy than the reactants, so that's an example of an exothermic reaction. So some key terms that we've already seen before is, first of all, enthalpy. That's the heat content, and it's got the symbol H. Delta H, delta is a Greek letter, and it stands for the change in something. So delta H is the change in enthalpy. And we've seen previously that endothermic reactions are reactions where energy is absorbed. So the delta H value is going to be positive, and heat is absorbed, so the temperature of the surroundings is going to decrease. So an example of that would be if I dissolve ammonium nitrate, or photosynthesis is another example, where energy is taken in, energy is absorbed. So if I dissolve ammonium nitrate, the temperature goes down. Exothermic reactions, they've got a negative delta H value. The reactants have a higher enthalpy than the products, and heat is released. So an example of that would be combustion. When I burn something, heat is released, the surroundings increase in temperature. Another really important concept, and it is somewhat counterintuitive, is that forming chemical bonds releases energy. So whenever we form chemical bonds, we release energy. To break chemical bonds, we need to supply energy. And another general trend that we need to be aware of is that generally large molecules broken down into smaller molecules, they're processes that are going to be exothermic. Now, another word for large molecules getting broken down into smaller molecules, that's called catabolic processes. And so those processes are exothermic. An example of that would be respiration. We've got the large molecule glucose that's broken down, and that reacts with oxygen, and it's broken down into smaller molecules of carbon dioxide and water. The opposite of that is where we've got small molecules that join up to form large molecules, and those processes are called anabolic processes. Now, a good trick to remember that is anabolic steroids. Bodybuilders use those to build muscles. So an anabolic process is one where we're building something bigger. So we're going from small molecules to large molecules. Now, those processes are endothermic, and an example of that would be photosynthesis. We've got smaller molecules of carbon dioxide and water that join up to make glucose and oxygen, and the glucose molecules are the ones that are larger. Now, another really important concept is specific heat capacity. Now, the specific heat capacity of a substance, that is the amount of energy that needs to be supplied to increase the temperature of that substance, to increase the temperature of 1 gram of that substance by 1 degree Kelvin. Okay, so an example of that would be water. If I've got 1 gram of water and I want to increase its temperature by 1 degree, I have to supply 4.18 joules of energy. Okay, and you can see that by comparison to other substances, water has quite a high specific heat capacity. So it takes a lot of heat to increase the temperature of water. Now, the equation that is on the screen right now is an equation that we're going to use quite a bit in this topic. Q is mc delta T. And that's an equation that we can use to work out the amount of heat that is released or absorbed in a chemical change. So Q is the quantity of heat that is either absorbed or released. M is the mass of the substance that is being heated or cooled. C is the specific heat capacity of that particular substance. And delta T is a change in temperature. So you can see that I've got an example here on the screen. If we wanted to find out how much heat is needed to increase the temperature of 50 grams of ethanol by 6 degrees, first of all, we need to know the specific heat capacity of ethanol, and I've looked that up before. It's 2.44 joules per degrees per gram. So to work out Q, M is the mass of ethanol, so that's 50 grams. That's what I've got here. times C, the specific heat of ethanol, which is 2.44, and the change in temperature is 6 degrees. And when I put that into a calculator, that gives me the answer 732 joules. Okay, here's another example that we're going to work through together. The specific heat capacity of toluene is 1.68 joules per degree per gram. 130 grams of toluene, increasing temperature from 26 degrees to 43 degrees. There's a mistake there. How much heat was needed? Okay, so Q is MC delta T. So M is the mass of toluene, which is 130 grams. C is 1.68. And delta T is 43 minus 26. So when I put that into a calculator, that gives me an answer of 3,713 joules. So it's going to be 3,700 joules or 3.7 kilojoules. Okay, now the other thing that we need to be aware of when we're doing this type of calculation is to be mindful of the units. On the data sheet that you will get for your HSC, the specific heat capacity of water is given as 4.18 times 10 to the power of 3 joules per kilogram, not grams, per degrees Kelvin. So you need to be very careful with your units, okay? So when you're working out Q, again we're doing MC delta T. But because these are the units that I've been given, I'm going to have to make sure that the mass is in kilos. So the sample has a mass of 50 grams, so that's 0.05 kilograms. The specific heat is 4,180. And the change in temperature is 16.5 degrees. So when I put that into a calculator, that works out to be 3,450 joules, which is the same as 3.45 kilojoules. Okay, now over to you. You need to have a go at doing lots and lots of examples of these calculations before we move on to the next concept.